Okay, let's get started. So, I want to tell you about a lot today. So I want to connect a lot of what we've been saying. So we've had about a week's worth of lectures on running algo and then some theory about Markov chains. And so this algorithm we're studying is a Markov chain, and it does something. And so I've also told you things that Markov chains do, always do. They always have and produce stationary distributions. So if I run some process, it will eventually sort out to, you start visiting states with some probability, and that probability doesn't depend on the starting value. And so that's actually what a limiting distribution is if it exists, the way that I explained it. The stationary distribution analog is that if I start drawing from that distribution, I sort it through my Markov process, it lands up in that same distribution, and that distribution doesn't move. All Markov chains have that distribution. And then I said some things when those two distributions, when the limiting distribution exists, it's stationary, and I said a criterion for when a limiting distribution exists. And I gave you some words for it. But really I said the process, the Markov process, it's just kind of exploring and wandering around the space, that if I can get from anywhere to anywhere, and the technical term is states communicate, all states communicate with each other, and I can get back to my original state in a finite amount of time, what that tells us is we'll eventually get everywhere. And so if that's true, then we might have a limiting distribution. We need one more condition, that I can get to anywhere eventually on any particular iteration of the process. And so it's random. It's a random process that can get from anywhere to anywhere. And so what Metropolis Hastings is it's a Markov process that we're clicking through. And eventually it arrives at some limiting distribution if it exists. I'll tell you this, if you've set up the code right, it will exist. And so all those three conditions will be true. And so what it means is we'll eventually start sampling by clicking through the limiting distribution from the stationary target, which in our case is our Bayesian posterior. Really neat thing, putting all that together. So this is incredibly different from what a lot of people do in stochastics classes. I'm going to try to write down everything I just said in a couple minutes. So we'll go through Metropolis, connected in conversation, and then I'm going to show you this very special equation called detailed balance. And this is the super equation in MCMC land. This is the special equation. If I want to show my algorithm works, then I have to adhere to this equation. I'll tell you what the equation means. I'm not going to go into one aspect of the equation, but it's pretty intuitive when you first write it down. I'll tell you the part that we're going to sweep under the rug. And then I'm going to tell you about a new algorithm called Gibbs sampling, and it's really a type of Metropolis Hastings algorithm. And it's the way that most Bayesians go through breaking up very high dimensional space and doing Metropolis Hastings on high space. And then I'll show you my code too, which really is a Metropolis Hastings buried within Gibbs algorithm. And that's what most Bayesians end up building up to. Once you know this sequence of algorithms, you're almost unstoppable. And so regardless if you can do all the math, you can still do the inference. If you know this and you can code it up properly. Homework 3 is out, so let me just show that to you real quickly. So it's online in the typical place. So just click on homework 3. I said that it would be due in 2 Fridays. So not this Friday, but next Friday. So one weekend in between. I think we can do a review session, a sequence of review sessions next week. That's probably more useful. If you need anything during this week, just send me an email. I can sit down with you. Do not do problems 1, 4, or 5. And so we'll get around to those later. So these are problems that concern distributions over matrices. So in previous iterations of this class, I taught that stuff before I taught the sampling. I actually want to teach this other stuff in the context of what we're learning right now. So this is a distribution over matrices. It's called a Wishart distribution. I'll teach you about it soon, but you don't need to do that problem. Instead, you're going to be doing this regression. So sort of problem. So we're going to extend on the regression problem that we've seen previously. And I'll show you how to do what's called a Cauchy regression. So if you have a whole bunch of data points and you want to fit a regression line through it, what we know from maybe our Stat 101 classes or some version of that, that if you have outliers, it will pull your regression line around. And so that has to do with the Gaussian assumption in the errors. So it has to do with that squared error penalty that we end up getting. And it pulls the line towards high residual points. So what we usually learn is get rid of all that stuff, pluck it off. What I'm going to teach you is leave all that stuff in the data set and build a robust regression and explain uncertainties, including those outliers. So I'm going to assume that outlying points aren't real outliers. It's just with respect to a normal distribution that they're outliers. It might be a whole different process. So we're going to take this idea with Cauchy distributions one step further and build our regressions that way. This terminology, full conditionals, will be clear after we get through Gibbs sampling. These matrix problems right here, these again are some matrix problems. You've probably seen this before, properties about traces. We'll need that when we discuss Wishart distributions. So if you need a quick reminder before we get into lecture, maybe look this stuff up. If you don't know what a trace is, remind yourself before we get to that lecture. And so, and problem 6 is to implement a Gibbs sampler that I'm going to tell you about later today. Problem 7 is a good practice problem. Find the Jeffreys prior for P. Let me give you a hint. In this class, take every distribution you know, one-dimensional distribution, and see if you can figure out what the Jeffreys prior is. And so you'll be good to go for the midterm exam. And so I'll pick something from the exponential family. Let's make it real easy. And so those all have Jeffreys priors. So work through all those calculations. Standard calculus problem. So this is just a motivator. I probably won't ask you to do this one. I'll ask you to do a different one. Okay, so that's the homework. So about 2 weeks on that, and then we'll start layering in those other problems later. Don't forget about it.
So those won't be due on this assignment at all?
That's right.
Okay.
And I'll make a note on the webpage. If you want to turn them in, I guess that's fine. I'll probably ask you to turn them in later as well. So if you do them, probably just hold them for a while. Okay, we'll come around to my code soon. I want to come back to this question I asked in the first week of class before we even go into details about Gibbs samplers and everything I just said. So we read this paper. So does anybody remember the author of the paper? So this is an important thing to do. Every time you read a paper, commit to memory who wrote that paper, what year it was done. So if you do that over your whole grad career, you're going to walk out with an archive of 500 papers in your mind. And that's probably 20% of being a scholar. So just being able to do that, oh, this person said this, and I remember what journal it was in. So some people make a whole career just off of doing that. So they usually have big, long gray beards. So 20% nowadays. So anybody? Stephen Feinberg. So anybody know where he taught? Carnegie Mellon. He's a powerhouse in the field. And so came up with a lot of Bayesian ideas, computational ideas. So one of the top 10 guys of his generation. And as he got a little bit older, he started thinking about the history of his field. Why do we do what we do? And so it brings you around to these sort of questions. Who even named this field Bayesian Statistics? It certainly wasn't Thomas Bayes. So again, we saw in the first week of class, he passed away before his idea caught on. So John Canton ended up relaying from Richard Price that message. So over to the Royal Society and it caught on. So let's go back to this. I think this was homework 0. What do you guys think? Maybe Fisher, yeah. So I've got a couple different questions right here. So who coined Bayesian stats? Who called it Bayesian stats? We used to call it like inverse probability. So that's what most people were calling it. So Laplace was calling it that. He didn't call it Bayesian stats either. So there's these two questions. Who creates the term? Who used it first is maybe the creator. And then there's always who popularized it? Who made it stick? And those are two different questions. So I think the answer is correct if you ask who said it first. He certainly didn't popularize the term. And so he said it in kind of a derogatory context. And so I don't think anybody paid attention when he first wrote it down. And so this Bayesian sort of thing. And so it was kind of a flip comment that he was making back in the 30s. And people weren't using the term for another 20 years. And so, but I think you're right. I think that's what Steve Feinberg discovered in his investigation, as Fisher had used the term, possibly first, but everybody that read through it never used the term afterwards. So I wouldn't say that he's responsible for it, but he certainly used it. So Fisher, after he got a little bit older, he started to sympathize with the Bayesians, but during that period, he didn't like anything that looked or felt Bayesian, even though his whole fiducial class of statistics looked and felt very Bayesian. He was trying to differentiate what he was doing, though. We don't have too many classes on fiducial statistics these days. So let's go back to this one. Who popularized it?
Rayford and Schleifer, I thought it was Wall.
There's a lot of answers to this question I always get, because that paper is long. And so he says a whole bunch of people are responsible for spreading it all. So if you skimmed it, the paper, you would have all these answers. So I don't think those are the answers. I think they got it from somebody else. And so that he's explaining the whole lineage of the term getting used and popularized. So I don't think they get credit, but they're certainly in the conversation. If you don't get other people to use the term, it's not going to be popularized. So they might be in the first tier of people using it, but I'm not sure that's not what I read when I read Feinberg's paper. And I had the great pleasure of meeting with them and talking to them about it, and also talking to one of the people that he gives almost most of the credit to. And so, and I asked him personally about how this all went down. So it's kind of fun, but it is all detailed in the paper. Anybody else? Sierra?
I'd say Savage.
Savage is a good answer. So I kind of like Savage. He's in one of my top 3 answers too. I think there's 3 really compelling answers to this, so I'll give you my 3. Savage is one of them. And so if you guys want to argue and go back, so I think it's all about usage. Popularization is a hard thing to really definitively say this person did it. Here's how I think it happened. I think De Finetti used the term. But not quite. He said something just a little bit different. So he wrote it in a title of one of his papers. Anybody remember this part of the paper? Over a month ago. He said this, Bayesian. So he wrote it differently. He's an Italian. He's a probabilist. And De Finetti will write about the foundations of Bayesian statistics, i.e. probability. If you're a probabilist, you probably like Bayesian stats because everything lives in a probability space. It's formal probability theory. So just likelihood times prior, once I go through those steps, I live in a probability space. So he used this term, Jack Good. Most people call him IJ. In academia, Good reviewed the paper. If you know of Jack Good through his writings, he really loves terminology. He's kind of humorous about things as well. He's pretty witty with words. And so this was a real curiosity to him. And so he thought it was pretty neat, but he thought it should be spelled Bayesian. And so wasn't aware that Fisher had written it down the same way. And so, and used the term. Jack was at Bletchley Park doing work with Alan Turing. If you read the book Imitation Game or go see the movie on it. So he was Turing's right-hand mathematician. So he was also a mathematician, Turing as well. And so they didn't really have the silo statistics yet. And so, but they were doing a lot of stats and they were doing a lot of Bayesian stuff, and Jack had written on that quite extensively. And so Butt wasn't using this term Bayesian quite yet. So he had reason to really like this term. I want to call what I've been doing something. And Jack he's really into this, so he would always publish with a fictitious co-author called Duke, because he liked using the word we. And so again, terminology and wording is extremely important. Duke, does anybody get it? Flip good around. So catch game. So this is first thing. But he uses the term and he shows it to Savage. So discusses with Savage. Savage is writing the foundations of statistics, his novel on all of this. Starts using the term there. And so it explodes. So who gets credit? Well, they all do in some way. But I think this is the way it happened. And then everybody that has other people that they want to extend into the argument, they're the ones that were the early people that started using the term, where they used it, why they used it, what they were working on. And that paper goes into a lot of citations. So it's pretty thorough, impressive work by our old colleague Steve Feinberg. So I think that's it. You can have your own version of the history, but there's support for all of these things. So I've discussed it both with Jack and with Steve, and I think this is what they were trying to say. It's just complicated. It goes on for 40 pages. So, any questions about that? Now we use the term. We take it for granted. So just kind of some fun stuff. So we've got a name for this thing that we do, likelihood times prior. And then in the 90s, everybody got sophisticated and they started saying, how do you sample from this thing because I can't do the math? So that's what Markov chain Monte Carlo is all about. So just write down stationarity one more time. So stationarity says this. So we're switching gears back to our algorithms and thinking about properties of Markov chains. So stationarity says for a Markov process, with transition, I'll write it down like this, maybe rho, that will take you in time between two states. So this might be our continuous version of this. Or in discrete land, we might write it down as a matrix. Where elements I'll write it down as A, I, J, represent the transition probabilities. And I'll just shortcut the notation because we've seen all that, of transitioning between I and J, states I and J. So the typical sort of thing. So stationary distributions have this property. And I'll call this thing pi. So this is my discrete notation. So that's just going to be a vector pi 1 down to pi, however many states we have. Or pi theta if we're continuous. So stationary distributions have this property. So in continuous land, it's going to be pi theta t. It's going to be the integration over the transition space after sampling from the stationary distribution for the starting location. discrete land, this is just this. A transpose pi is equal to pi. So we solve for that. We also need that pi sums and integrates to 1. So they're really the same thing. So what this says is if I sample out of the stationary distribution, I walk it through my Markov process, I come back to the same distribution governing theta, but I'm at a different location. And so this function and this function are the same. I'll point out that in the burn-in process of Metropolis Hastings, that you'll recall from our simulations, when it's not stationary, this thing is changing as it steps through the process. Once it hits pi, it stays there. And so in burn-in, this is a different function. So I sample out of it, I walk through my distribution, I come to a different distribution. I keep doing this over and over and over again, and eventually this settles down to the same distribution. So in burn-in, it's not stationary yet. We're not sampling from the right target. This is the discrete way of writing that down. Limiting distributions are a little bit different. And so limits. And I'll write it down in the discrete case, are just a to the n limit. N goes to infinity. So an that we've learned is the n-step transition probability. It's just linear algebra. What I'm going to do is I'm going to take this to the limit. And if this equals to something where the probabilities in, I'll say state 1 right here, all the way to state S, that's my total number of states, if these converge to the same numbers, then a limiting distribution exists. So this is where we're coming from, and this is where we're moving to. So if the probabilities of being in a state become the same after n steps, regardless of where we started from, the limiting distribution exists. So limits exist if all states communicate, the expected arrival time back to your starting locate, back to any state that you start from in the stationary distribution is finite. So expected time of return is finite. And there's no funny patterns. This is an eventually statement. Eventually, we can explore states on any iteration of the process. Just to be clear about this, it could be that for the first few steps of your Markov process, depending on where you're starting from, you can only see a particular state on like the third or fourth step. You would never be able to get there on the first one. And so this is an eventually thing. If eventually you could get there on any multiplier, then this condition would be true. So the eventually part is important. This is called aperiodicity. Let's see if you guys remember. What's that one called?
Irreducibility.
Irreducibility. So I don't get trapped in a space and I reduce the whole exploration to just one part of the space. That's what it means to be irreducible. So I can't reduce and get trapped in a part of the space. Irreducibility. That's the technical term. And this one, expected time of return is finite. Positive recurrence. If this doesn't happen, we call it null recurrence. So there's names for all these things, and if a mathematician named it, it's probably pretty well named. So it probably means exactly what words say that it means. So those are the conditions. Really, it just says I can get from anywhere to anywhere. In some finite amount of time, I will. And I don't have funny patterns, i.e. this is random. And then the stationary distribution and the limiting distribution are the same things. So I think we've said that a whole bunch of times. So that's cool. But it's important. Here's how we exploit it. Here's what we do with all this math. So this is a big deal. So my goal is going to be to sample thetas from our Bayesian model. I like to write it down like that. That's our posterior. So Bayesians are just building a distribution on parameter space. How do they do it? They take the likelihood function and they multiply it by prior. In all of this, I'm assuming you can write that down. You can write down the mathematical description of the prior, and you can write down the mathematical description of the likelihood. In more complex modern schemes, you can't actually physically write it down, but we have other computational layers to deal with it. Hopefully we can get into some of that. So, likelihood times prior. That's what Bayes is. So some people do regularized likelihood. So some people do penalized likelihood. This is a form of penalized likelihood. And so we interpret it as a probability distribution once we get it. So we want to be able to do this. This might be hard. This might be high dimensional. It might be complex. We might not have a button built into R for doing it. We can't get perfect samples, but I can step through a limiting process, a Markov limiting process that does eventually sample from this thing. This is beautiful. If I can always do that, then I'm in business and I can answer any questions about this distribution if I've got samples from it. So here's how we do this. 4t goes from 1 to some big number. Big is always relative to how complex the space is. I'll show you diagnostic methods to at least help you convince yourself whether you've actually run it long enough. So there's 2 steps in here. So I will mention there's always an initialization step as well. So this is an iterative algorithm and we have to kick it off somewhere. So step 0 is to set, I'll say theta 0. And theta can be anything you want, anything that you don't know, and you want to put a probability distribution on it. So a lot of times we're thinking of them as continuous numbers or something discrete, but they can be anything that your mind can imagine. So, and then the power of Bayes really starts to flow through this. So step 1, step 2. So what we do is we propose. So theta star gets proposed from some proposal function. So it's a Markov process, so the whole process, everything I do can only be Markov. I can't consider 2 steps back. What we've talked about in the last couple times is I don't even have to condition on anything. I can let this be an independent proposal. And if it covers really well where your target is, this might be a good way to do that. It probably wouldn't be your best algo. If that were the case, if you had something like that, we could probably do better. But proposal distribution, so e.g., maybe our local proposal is G theta star given theta t minus 1 might be equal to 1 over 2 pi. If this was a one-dimensional thing, I've got some tunable variance, e to the minus 1/2 theta star minus theta t minus 1 squared psi squared. So this is what we've been thinking about, at least for updating mu in our normal distribution. This is what we talked about. So this is the what have you seen lately sort of proposal strategy. It also has advantages that it's symmetric. So step 2 is your decision. So this is propose. And then you decide. So alpha, the decision rule in this algorithm is 1, minimum between 1, my posterior target that I can write down, at least up to proportionality. So my target ratio of where I'm moving to and where I'm coming from. But I need to account for my proposal, and so if I'm not willing to go back to where I'm coming from very often, I would say stick around for a little while. If you're not welcome back, you might want to hang out. And that's what this rule says. And then I just update accordingly. So theta t is going to be theta star or theta t minus 1. This happens with probability alpha, 1 minus alpha. So apologies to Susan in the back. We've talked about this algorithm 5 times. We've written it down. And so this is just a reminder. But again, what this rule says is that if where you're proposing to is high relative to where you're coming from, at least in the model, maybe move there. But be careful that you can come back to the old location given if you actually did take the step. And so this is really just good life strategy. And so try to check things out and make sure you're welcome back to where you're coming from. And so good proposals can explore the space very nicely, come back to the different parts of the space that maybe have high mass, but also exploit good stuff that they found. So if you've seen some good stuff around there, stick around for a little while. And so that's how we manage our lives quite often.
Excuse me, why did we say in step 1 that if we're proposing a certain G, it doesn't have to be conditioned? It can...
Yeah, if I write down the rule, so let's say I did this, I didn't have any conditioning. I'm just going to get rid of my conditioning here in the model. So these can be independent proposals as well. It's the same algorithm.
But how would it impact the algorithm?
Depends on what the target is. So Christina's going to ask me the same question over and over and over again. How does G impact the answer? And it determines the whole algorithm that you're using. That is the whole question. So here's the whole field of Metropolis Hastings. Different types of distributions, so multimodal distributions. I wouldn't use a local proposal there. I need something fancier to get me around the space. So I'll tell you about my proposal strategy later. So things that look like boomerangs. So distributions that maybe look like this. So joint distributions between 2 parameters. So they kind of pull in weird directions, and a local strategy wouldn't be very good because I would have to move very slowly down here. And then I'd have to change my whole proposal mechanism, the direction of it, to explore over here. So all of these algorithms differ by G. So how will they impact everything? That's what the homework's all about. I'm going to have you test out some different stuff. And you're going to answer back to me how it affected things. And so good G's can get around the space fast. Different targets have different properties, so getting around those spaces fast need different strategies. Make sense? It's a whole field, and that whole field differs by this line. How does that change? Well, let's go through the whole book of algorithms. I'll give you more exhaustive strategies. So we're just getting started. Okay, so that's the algorithm. I want you to just look at this real quick. This is a Markov process. It's going to limit to something. What I say it limits to is the posterior distribution. So fact. Metropolis Hastings, Markov process, limits to sampling from pi theta. And if you haven't picked this up yet, I can plug any distribution in there, any shape. It doesn't have to be a Bayesian model. So this is a general purpose sampler, and a lot of Bayesians go running after it because I can plug in any model right there. And if G is well constructed, it'll work. So again, how do you well construct G? You tell me pi, and I'll start to think about the hundreds of different versions of this I know. I'm going to probably teach you a dozen of them. So this is a if sort of thing, if a couple things happen. And so somebody help me out real quick. What has to happen in this algorithm for this thing to limit to the stationary target? So I'm telling you that if it limits to something, it'll limit to that.
This ratio should be 1, right?
What's that?
The ratio that we have here should go to 1.
It should not go to 1. It'll bounce all over, and this will be a distribution. Some strategies for G will always produce a acceptance probability of 1, but it doesn't actually converge to that. And so high acceptances, too high of acceptances can be bad strategies as well. High acceptances can be really good strategies. So we have to be careful. But it turns out I can go either way on this. It doesn't need to limit to 1. So just think about our properties of limiting distributions. What do we need for a limiting distribution to exist? So I am telling you this, the fact, if it limits to the right thing, if this is set up right, we'll eventually sample from this. But a few things need to happen. I need to get a G that can at least jump around my space and travel from anywhere to anywhere. It's able to explore everywhere. So if G explores the whole space, and I should say can explore the space. So if I had a proposal mechanism that only sampled from positive real numbers and pi theta lived on the whole continuous real number line, I could take negative values, and I'm not willing to propose over there, well, I won't converge to the right thing. No great surprise. So that's what I mean right here is I need to be able to place mass on the whole space in which pi lives. If I'm going to explore that thing and sample from it, I better be able to get around there. So G's got to be placed correctly. So that's not hard to do. You'd be able to figure that out real quickly. So what about the finite return sort of thing? And so we need to convince ourselves that we have a finite expected amount of return. We'll show that using an equation, that this just happens for us. But return time is finite. Now, if I had a G that was drifting and moving all over the place, I don't have any guarantees on anything. But if G can get me from anywhere to anywhere, and I'm just sampling and proposing from this distribution that isn't moving, then I'll come back eventually. So I was there once upon a time, so I'm going to come back. I'm using the exact same mechanism to do it. So if G isn't wandering around, and it's not in this, there are adaptive strategies that allow that for a while. So that's just engineering though. Then I'm going to come back. So it seems like we've got it. What about the no funny patterns and aperiodic? how do I know this thing is aperiodic? If all of this produces, so I'm not saying G is aperiodic, I'm saying the process, the whole thing is aperiodic. How do I know that that happens? There's actually a really simple reason for it in this algorithm.
Coin flip?
What's that?
A coin flip?
It's a coin flip, yeah, absolutely. You got it. So David's spotting the right part. There's a positive probability I stay in the same location. And so if I can always stay in the same location for a step, well, that will make every state aperiodic. I could stay there on any particular increment. So we could prove that mathematically, or you can think about it for a moment. And so I'd encourage you to do both. But that's actually the reason why this is aperiodic. So if G is well constructed, and it's not moving around, this thing will work. I need to show you a very important equation before I can actually prove that the stationary distribution is pi. So I've said so far, stationary distribution is pi in this thing if G is well constructed. How do you well construct G? Make sure that it places positive mass on parts of the space that you want to explore, and we'll get all three conditions automatically. So it turns out the limit exists here. If you wanted to make the limit not exist, put G somewhere and make sure that it doesn't put mass on part of the answer in pi. And then you would make the limit not exist. So that's kind of nice. This process has a limit. So here's a very important equation. I'm going to call it the super equation. And it says this. I'll write it out continuously. Rho theta t given theta t minus 1. So this is a Markov transition. Just ask a question real quick. For Metropolis Hastings, our transition rho theta t given theta t minus 1. I've said it in class, but I've never written it down. What is it?
Alpha times G.
Alpha times G. All you have to do, you can't answer the question unless you stare at the algorithm. So what's the probability or rate? If G is continuous, if pi is continuous, this thing is continuous, and to discuss it as a probability wouldn't be the right thing to talk about because the probability is always 0. But the rate of transitioning is determined by these two conditionally independent steps. Obviously, alpha is conditioned on step 1. And so how do I look at the joint rate of something that's conditionally independent? I just product them together. And so this is just going to be alpha times G. Theta t given theta t minus 1.
So this is a rate more than a probability?
If G were a probability, this would be a probability. If G is continuous, well, it's got this continuous element to it. So the probability of transitioning in continuous space is 0. So, yeah. So this is our rate. So I call it transition rate. Cover both words. So it's alpha times G. If you'd like, I could probably butter up my notation and say this alpha acceptance probability changes with arguments of theta. I'll probably write it down there next time when we do some proofs with it. But it's just alpha times G. So let me just show you something important about this. So here's my super equation. Times pi theta t minus 1 is equal to rho theta t minus 1 given theta t pi theta t. just going to write this down as a concept for a moment. So if I write down this equation, I don't know, do you believe me? And when I ask, do you believe me, this equals sign. Yeah, and he's like, what the heck, man, super equation? I know that equation, right? Because, you know, if rho are continuous, I know what that equation is. I even know what pi is. Pi is the margin of that conditional distribution. That's what it says. So this is usually considered the margin of this thing. These are usually considered conditional distributions. And they are. That's what it is. And so it's pretty easy to swallow if you know anything about joint probability land that this should be true. This has a name. It's called detailed balance. So nobody in the world called it super equation until today. And its real name is called detailed balance. Here's what we do with this equation. So I can almost hand this to you and make you accept instantaneously that pi is the stationary distribution. And rho is just my Markov transition. There's one part I'm not telling you about, and it's actually this part right here. This is the reverse transition. So the algorithm's running in one direction, right? This is asking what happens if I ran the algorithm backwards. Is it the same thing? Are these the same? And it turns out if they're the same processes, we say the process is time reversible. And not all Metropolis Hastings algorithms are totally time reversible. They're time reversible if that rho function is the same for going in both directions. So there are Markov processes that are not time reversible. There's a lot of physical processes that are not time reversible. So just as a concept, let's think about time reversibility in a mathematical way. So I'll tell you about a process that is not time reversible. Melting a candle and understanding what the candle looks like. So if I take a candle, one of these old candles, we probably don't have them anymore, that just blobs their wax all over the thing if it doesn't evaporate. So old candles, I could light one, and I could have this big, long candlestick, and it becomes a blob. And so I can tell you probably what the blob's going to look like. I can simulate that for you. I could have a candle that looked really cool, like a motorcycle or something with a wick coming out the top. And I light it on fire, and it makes a blob. And I could probably tell you what the blob was going to look like. It would probably look a lot like the same blob that would have formed under the big, long candlestick. What I can't do is I can't look at the blob and tell you what the candle looked like. And so that's a non-time reversible process. So these four diffusions. So there are Markov processes that are time reversible. We'll get into it. It's not all that important in terms of running this thing. And so that's the only part that's not obvious about this equation. Otherwise, it just looks like what we learned in Stat 101. And so how do I prove G is the stationary distribution? Pretty easy. Or sorry, pi is stationary. So I would just say something like this. I'm going to integrate both sides. Let's do it like that. I'm going to integrate, and I'm going to integrate. I got to be careful, and I got to integrate both sides with respect to the same thing. Can't integrate with respect to something different. So this is pi of theta t minus 1. Notice this isn't on theta t right here, so I can slide this outside of the integrand right here, and then I'm just integrating over that function. This one, however, has theta t minus 1 popping up in both arguments, so I can't do that so easily. So this is rho theta t given theta t minus 1 pi theta t minus 1 d theta t minus 1 is equal to, I slide this thing outside of the integrand, and then I integrate over rho. So this is going to look like pi theta t minus 1 integral rho theta t minus 1 given theta t. Somebody help me out on this integral. I'm not too swift.
1.
It's 1. That's the random variable right there. If I integrated over theta t right here, that wouldn't integrate to 1. If I integrate over the random variable, it integrates to 1. So this thing right here, you don't even have to write down. It's 1. So it's just this thing right here. Does this look familiar? That's my definition of stationarity that we just used. So detailed balance, if I can write it down,
So you have a typo, right? It should be theta t, pi theta t.
definitely. Yeah, that's kills the whole thing right there. But yeah. Yeah, that's the definition of stationarity. So that's what we've got right there. And so if I can write down what my transition probability is, and we can for this algorithm, and then I can verify this equation right here where I plug in my stationary target being the Bayesian model and show that that's equal, then I know that it's sampling from the right thing. So it's that simple. So this super equation, I always build algorithms. I take whatever my transition rules are, I plug them into the super equation, detailed balance, and I make sure that it's equal on the left and the right-hand side. If that's true, it tells me what rules I'm using to transition around the space will eventually converge to the posterior target, samples from it. And that's really very cool. And so why do I construct different rules? Well, if I happen to know about what that space might look like, I can probably get around it faster if I have more sophisticated rules. So that's really the answer to Christina's question. It's usually we end up checking this, making sure the G we're using gets us around the space, adheres to this, and then usually we look for efficiency out of it as well. So you either run the simulator and see that it runs faster, or you do some math and you prove it. So let's come back next time, discuss in 2 minutes what a given sampler is, and then I will finally show you all of my code, and I'll divulge this thing to you as to the problem that we're solving. On Friday, Sierra's going to teach, and she's going to tell you how to do this for mixture models, which, if there's one thing you can pick up in graduate school, it's how to sample from mixture models. If you can do that, you can almost write a PhD on it, depending on which department you're in. So back in the 90s, this was an excruciatingly difficult problem for people to work with. Now it's a homework assignment. So I'm going to have you do it. So Sierra will give that lecture on Friday and Monday. Thanks, you guys. That's it for now.